In an era when a single reconnaissance photograph can unravel an entire offensive operation, and when the electromagnetic spectrum has become as contested as physical terrain, the appearance of platforms like the CS-5000T stealth drone represents not merely an incremental improvement in aerial surveillance capabilities, but rather a fundamental recalibration of tactical doctrine. This is military technology where the difference between a radar cross-section of 0.01 square meters and 0.001 square meters can mean the distinction between mission success and a smoking crater in hostile territory, where every composite panel must be manufactured within tolerances measured in hundredths of a millimeter, and where the failure of a single bolt in a control surface actuator can transform a multi-million-dollar asset into an expensive lawn dart. The CS-5000T, despite its somewhat corporate-sounding designation that suggests it might equally be a commercial photocopier or an industrial refrigeration unit, represents an attempt to compress the capabilities of strategic reconnaissance platforms into a package deployable at the tactical level, bringing stealth characteristics previously reserved for high-altitude strategic systems down to the operational ranges where battalion and brigade commanders make decisions that determine whether advances succeed or collapse. The fundamental architecture of the CS-5000T follows design principles established by earlier stealth unmanned systems, but implements them at a scale and with an integration philosophy that distinguishes it from both larger strategic platforms and smaller commercial derivatives pressed into military service. The airframe measures approximately 4 meters in wingspan with a fuselage length of roughly 3 meters, dimensions that place it in an operational sweet spot between man-portable tactical drones that offer limited endurance and payload capacity and larger theater-level assets that require dedicated launch and recovery facilities. The aircraft employs a blended wing-body configuration where the fuselage gradually transitions into the wing structure without distinct demarcation, a geometry that reduces the number of angular discontinuities that create radar returns and provides inherent aerodynamic efficiency by distributing lift across the entire planform rather than concentrating it in conventional wing structures. This configuration, while aerodynamically advantageous and electromagnetically desirable, presents manufacturing challenges that explain why the unit cost of such platforms inevitably climbs into ranges that make logistics officers wince, and procurement officials develop nervous tics when budget committees begin asking uncomfortable questions about program expenditures. The structural composition relies heavily on composite materials, specifically carbon fiber reinforced polymers combined with radar-absorbent materials integrated directly into the layup, rather than applied as external coatings that can degrade or delaminate during operational use. The primary load-bearing structures utilize unidirectional carbon fiber pre-impregnated with epoxy resins that are cured in autoclaves under precisely controlled temperature and pressure profiles, a manufacturing process that sounds straightforward until one considers that variations of even 5 degrees Celsius during cure cycles can compromise structural integrity sufficiently to require complete component rejection. The outer surfaces incorporate honeycomb core sandwich panels where thin carbon fiber face sheets are bonded to aramid fiber honeycomb cores, providing excellent stiffness-to-weight ratios while creating internal volumes that can be filled with radar-absorbent materials tuned to specific frequency bands. These materials typically consist of carbon-loaded polyurethane foams or ferrite-impregnated polymers that convert electromagnetic energy into heat through dielectric and magnetic losses, effectively making the airframe disappear across radar frequencies from approximately 2 GHz to 18 GHz, the bands most commonly used by search and tracking radars. The propulsion system centers on a small turbofan engine, rather than the electric motors common in smaller tactical drones or the turbojets found in larger systems, a choice that balances endurance requirements against acoustic signature considerations. The engine, likely producing somewhere in the vicinity of 200 pounds of thrust, features a serpentine inlet duct that prevents radar waves from directly illuminating the compressor face, which would otherwise act as an exceptionally effective radar reflector, given that rotating metal blades present an ideal target for Doppler detection systems. The exhaust nozzle is similarly treated, incorporating ceramic matrix composite components that withstand the thermal environment while providing radar-absorbent properties, and features a flattened profile that spreads the exhaust plume to reduce infrared signature when viewed from below or behind. The fuel system carries approximately 60 kilograms of JP-8 or similar military jet fuel, providing endurance in the range of 6 to 8 hours, depending on mission profile and payload power requirements, which translates to operational radiuses that allow battalion-level commanders to maintain persistent surveillance well beyond direct line-of-sight distances. Navigation and control systems represent where the CS-5000T diverges most significantly from commercial drone platforms and smaller military tactical systems. The AI autopilot, which the designation highlights as though artificial intelligence were still a novelty, rather than an increasingly ubiquitous element of military systems, incorporates a flight control computer processing inputs from redundant inertial measurement units, GPS receivers with anti-jam capabilities, radar altimeters, and a suite of optical sensors that enable terrain-relative navigation when GPS signals are denied or unreliable. The artificial intelligence component handles not merely routine flight management tasks like altitude hold and waypoint navigation, which even relatively unsophisticated autopilots manage competently, but rather implements more complex behaviors, including automatic threat avoidance, dynamic route optimization in response to evolving tactical situations, and autonomous targeting and engagement sequencing when operating in strike configurations. This last capability introduces complications that make lawyers specializing in the laws of armed conflict reach for anxiety medications, given that autonomous weapons systems raise questions about human supervision of lethal force application that remain incompletely resolved in international law and military doctrine, though operational commanders facing overwhelming sensor data streams and decision timelines measured in seconds rather than minutes tend to have less philosophical patience for such debates. The sensor package represents perhaps the most critical element determining the CS-5000T's operational utility, given that a stealth platform that cannot collect actionable intelligence or accurately prosecute targets becomes merely an expensive method of delivering fuel to enemy territory. The primary sensor is an electro-optical and infrared turret mounted in an internal bay to maintain radar cross-section minimization, featuring multiple cameras covering visible wavelengths, near-infrared for low-light operations, and thermal infrared for true night capability and detection of heat signatures. The optics likely include a narrow field of view camera with sufficient focal length to achieve ground sample distances measured in centimeters from operationally relevant altitudes, allowing identification of individual personnel and equipment rather than merely detecting their presence. The turret gimbal system provides stabilization that compensates for aircraft motion and atmospheric turbulence, utilizing gyroscopic sensors and fast-acting electric motors that maintain line of sight on targets even during dynamic maneuvering. Though this stabilization system represents yet another component requiring regular calibration and maintenance by technicians who presumably did not join the military because they enjoyed troubleshooting temperamental precision mechanisms. The synthetic aperture radar system, integrated into the forward fuselage section, provides all-weather reconnaissance capability and ground-moving target indication, functioning by coherently processing radar returns collected over multiple transmission and reception cycles as the aircraft moves relative to the target area. This processing exploits the relative motion between sensor and ground to synthesize an aperture far larger than the physical antenna, achieving resolution that would otherwise require prohibitively large antenna structures. The radar operates in X-band or Q-band frequencies, balancing resolution requirements against atmospheric propagation characteristics and antenna size constraints, though the specific implementation details remain subject to classification levels that prevent discussing them in contexts where adversaries might benefit from such knowledge. The system can map terrain with sufficient resolution to identify vehicle types and detect changes between successive collection passes, enabling detection of new fortifications, repositioned equipment, or other indicators of tactical movement. Ground-moving target indication mode tracks vehicles and potentially even individual personnel through Doppler processing that distinguishes moving targets from stationary background clutter, providing battlefield situational awareness that transforms tactical decision-making when commanders know not only where enemy forces are positioned, but where they are moving. Electronic warfare capabilities integrated to levels dependent on specific operational requirements and the customization options selected by acquiring military organizations, provide both passive signals intelligence collection and active electronic attack functions. The Signals Intelligence Suite monitors electromagnetic emissions across a broad frequency range, identifying and geolocating radar installations, communications networks, and other emitters that betray force dispositions and operational patterns. Modern battlefield electromagnetic environments contain such dense collections of emissions that simply detecting signals provides limited value without sophisticated processing that correlates emissions with known systems, tracks emitter movements, and identifies changes in electromagnetic order of battle that indicate operational preparations. The electronic attack capabilities, when fitted, allow jamming of adversary communications and radar systems, creating localized denial of spectrum access that can be precisely timed to support tactical operations, though employing active jamming from a stealth platform represents something of a contradiction, given that transmission of high-power electromagnetic energy tends to make the transmitting platform conspicuously obvious to any receiver within line of sight. Weapons integration transforms the CS-5000T from a reconnaissance-only platform into a strike asset, though the internal weapons bay dimensions necessarily constrain ordnance options given that maintaining low radar cross-section requires keeping munitions contained within the airframe until release. The weapons bay likely accommodates 2 to 4 small precision-guided munitions with total payload capacity around 40 to 60 kilograms depending on configuration. Munitions options probably include variants of laser-guided rockets, small-diameter guided bombs, or specialized weapons optimized for the size and weight constraints of compact drone platforms. The guidance approaches span laser designation, requiring either the launching platform or another asset to illuminate the target with laser energy. GPS-aided inertial navigation for attacking fixed coordinates, and potentially electro-optical infrared seeker heads that allow autonomous terminal guidance against mobile or relocating targets. The weapons release sequence requires precise coordination between flight control systems, weapons bay door actuators, and munitions ejection mechanisms with timing accuracy measured in milliseconds to ensure munitions clear the aircraft cleanly without aerodynamic interference that could compromise either weapon trajectory or aircraft stability. Launch and recovery operations for the CS-5000T require infrastructure that balances operational flexibility against the handling requirements of a precision stealth airframe that costs substantially more than the vehicles typically used to transport it. Launch options likely include pneumatic catapults or rocket-assisted takeoff from rails, avoiding the need for runways while imparting sufficient velocity for the turbofan engine to generate thrust and the wings to develop lift. Though anyone who has witnessed catapult launch systems in operation understands that the apparent simplicity of accelerating objects along rails conceals remarkable complexity in terms of precisely controlling acceleration profiles, release timing, and recovery after launching what amounts to a mechanical slingshot designed to hurl expensive objects into the sky. Recovery typically employs either parachute descent into net systems or potentially skid-based conventional landings on prepared surfaces when available, each approach presenting distinct advantages and complications. Parachute recovery allows operation from locations without runways, but subjects the airframe to landing forces that accumulate structural fatigue over operational lifetimes. While conventional landings provide gentler touchdowns but require surface preparation and approach clearances that may not exist in forward tactical environments. The ground control station, which could equally be described as the neurotic center where operators simultaneously manage mission execution while preventing their expensive robotic charges from committing aviation equivalents of suicide, implements interfaces that attempt to reduce cognitive workload while providing comprehensive situational awareness and command authority. Modern implementations utilize multiple high-resolution displays presenting sensor imagery, aircraft status information, tactical overlays, and threat data, all integrated into an operational picture that ideally enables intuitive understanding without overwhelming operators with data. The control interfaces balance automation and manual authority, with the artificial intelligence managing routine functions while operators maintain supervisory control and decision authority for critical actions, particularly weapons employment. The communication links employ frequency-hopping spread-spectrum waveforms with encryption to resist interception and jamming, though maintaining reliable data links with a low observable aircraft that deliberately minimizes its electromagnetic emissions presents inherent contradictions that systems engineers address through directional antennas, careful frequency selection, and transmission power management that balances connectivity requirements against electronic detectability. Operational employment doctrine for systems like the CS-5000T continues evolving as militaries integrate capabilities that were previously unavailable at tactical echelons and develop tactics that exploit these new possibilities. The persistent surveillance capability allows maintaining continuous observation of key terrain, avenues of approach, or suspected enemy positions for extended periods, detecting patterns and activities that brief glimpses from faster-moving or shorter endurance platforms might miss. The stealth characteristics enable operation in environments where conventional drones would face immediate detection and engagement, penetrating into defended areas to collect intelligence directly rather than remaining at standoff distances observing through limited apertures. The strike capability provides tactical commanders with responsive kinetic options against time-sensitive targets, without requiring tasking of larger aviation assets that may be committed elsewhere or unable to respond within the narrow windows when opportunities present themselves. Though this same capability raises questions about whether providing increasingly autonomous strike systems to progressively lower command echelons might lead to uncoordinated actions that undermine operational coherence. Maintenance and sustainment requirements for the CS-5000T reveal the costs embedded in operating sophisticated military systems far beyond initial procurement expenditures. The turbofan engine requires periodic inspections, scheduled component replacements, and eventual overhaul or replacement after accumulating flight hours. Procedures that demand specialized tools, trained technicians, and supply chains that deliver parts to locations where such amenities may not naturally exist. The composite airframe, while offering structural efficiency and stealth properties, presents damage repair challenges given that field-expedient patches rarely restore radar cross-section characteristics even when structural strength is adequately addressed. The sensor systems require calibration and alignment procedures that verify optical bore sight accuracy, radar timing precision, and targeting coordinate accuracy. Tasks requiring test equipment and technical competence that battalion-level maintenance organizations may not organically possess. The reality of military logistics being what it is, operational availability rates for complex systems deployed to forward locations inevitably fall below peacetime expectations as spare parts inventories deplete, maintenance man-hours exceed available capacity, and the accumulated minor failures that individually seem manageable collectively degrade fleets to fractions of nominal strength. Comparative analysis against analogous systems reveals the CS-5000T occupying a capability niche between different categories of unmanned aircraft rather than directly competing with specific existing platforms. Larger strategic reconnaissance drones like the RQ-170 Sentinel or the RQ-180 provide superior endurance, payload capacity, and sensor capabilities, but require infrastructure and operational coordination that makes them theater-level assets unavailable for routine tactical tasking. Smaller tactical drones used extensively by ground forces offer excellent deployability and ease of operation, but lack the survivability, range, and sensor performance for missions in contested environments against capable adversaries. Commercial quadcopter platforms adapted for military reconnaissance provide immediate availability and simplicity, but survive only in permissive environments where adversaries lack even basic air defense capabilities. The CS-5000T attempts to bridge these gaps by providing stealth survivability, tactical level range and endurance, and meaningful payload capacity in a package that division or brigade commanders can task directly. Though whether this niche proves operationally significant or represents a solution seeking problems depends heavily on specific conflict characteristics and adversary capabilities. Potential modernization pathways for the CS-5000T design follow trends visible across military aviation, focusing on improved materials, enhanced sensor performance, increased automation, and expanded networking capabilities. Materials development continues producing composites with improved strength-to-weight ratios, damage tolerance, and environmental durability, potentially enabling airframe weight reductions that translate into increased fuel capacity or payload margins. Sensor technology advances steadily toward higher resolution imaging, improved target detection algorithms, and multispectral fusion that combines data from different sensor types to extract information no single sensor could provide independently. Automation and artificial intelligence capabilities expand beyond flight management and sensor operation toward increasingly sophisticated mission planning, threat assessment, and even engagement decisions. Though each step toward machine autonomy in lethal applications reignites debates about appropriate human control over use of force. Networking capabilities increasingly emphasize mesh topologies, where multiple platforms exchange data directly, rather than routing everything through ground stations, creating resilience against communication disruption and enabling coordinated behaviors where groups of drones cooperatively prosecute missions rather than operating as independent units. Counter-stealth technologies continue advancing in parallel with stealth capabilities, creating ongoing cycles where detection improvements drive signature reduction measures that prompt detection enhancements in endless technological competition. Low-frequency radars exploit the fact that radar-absorbent materials and shaping optimizations designed for higher frequencies become less effective as wavelengths approach and exceed aircraft dimensions, though these longer wavelengths sacrifice the resolution necessary for fire control quality targeting. Passive detection systems that monitor for electromagnetic emissions from the aircraft's own sensors and communications links can detect targets without betraying their own locations through active transmissions, exploiting the reality that maintaining situational awareness requires transmitting or receiving signals that can be intercepted. Infrared search and track systems scan for the thermal signatures that even carefully designed propulsion systems emit, potentially detecting aircraft through channels independent of radar cross-section. Acoustic sensors can detect jet engine noise or aerodynamic sounds at shorter ranges, particularly during approach phases when aircraft altitude and velocity reduce acoustic propagation distances. The effectiveness of any stealth platform ultimately depends on the specific sensor capabilities it faces, the tactical geometry of detection attempts, and the environmental conditions that affect electromagnetic and acoustic propagation in ways that sometimes favor attackers and sometimes favor defenders. The doctrine surrounding reconnaissance-strike complexes, of which the CS-5000T represents a tactical scale instantiation, emphasizes compressing the time intervals between target detection, decision-making, and engagement to durations that prevent adversaries from reacting effectively. Traditional kill chains involve multiple sequential steps where reconnaissance assets detect targets, information transmits through command hierarchies, decision authorities approve engagement, strike assets receive tasking, weapons deploy, and effects assessment confirms results. A process measured in minutes to hours that allows mobile targets to relocate and adaptive enemies to implement countermeasures. Integrated systems that combine reconnaissance and strike capabilities within single platforms or tightly coupled platform pairs reduce these timelines dramatically, potentially achieving detection to engagement intervals measured in seconds or minutes rather than hours, though this compression creates risk that erroneous targeting data or misidentified targets receive kinetic responses before human operators adequately verify target identification. The balance between responsive engagement of fleeting targets and measured deliberation to prevent fratricide or civilian casualties remains one of the central tensions in modern military operations. Electronic warfare implications of operating stealth reconnaissance strike platforms in contested environments extend beyond the immediate aircraft capabilities to encompass the entire sensor-to-shooter architecture. Communication links between aircraft and ground stations create electromagnetic paths that sophisticated adversaries can potentially exploit through jamming, spoofing, or cyber attack, disrupting command and control relationships even when the aircraft itself remains physically undetected and functional. Data links transmitting high-resolution imagery or radar products consume bandwidth that may be scarce in tactical environments where multiple systems compete for spectrum access, forcing compromises between sensor resolution, update rates, and the number of simultaneous platforms supportable. The electromagnetic signatures created by transmitting reconnaissance data potentially betray aircraft locations to direction-finding systems even when the radar cross-section successfully evades detection by conventional tracking radars, creating scenarios where successful sensor operation paradoxically enables enemy targeting. Managing these electromagnetic conflicts requires coordination across frequency planning, transmission scheduling, antenna directionality, and power management that transforms spectrum usage from an afterthought into a central element of mission planning. Training requirements for operating platforms like the CS-5000T extend well beyond the procedural skills of launching, flying, and recovering the aircraft to encompass the cognitive skills of exploiting sensor data and making tactical decisions under time pressure and uncertainty. Operators must develop expertise in interpreting electro-optical, infrared, and synthetic aperture radar imagery under varying environmental conditions, distinguishing between targets of interest and background clutter that can appear deceptively similar. Understanding terrain effects on radar propagation, atmospheric influences on infrared signatures, and vegetation impacts on target obscuration requires both technical knowledge and experiential learning that accumulates through extensive practice. Tactical judgment about when to engage targets, when to maintain surveillance for pattern analysis, and when to disengage before detection risk becomes unacceptable involves decision-making skills that cannot be reduced to procedural checklists, but rather developed through experience and guidance from more seasoned operators. The artificial intelligence systems, regardless of their sophistication, remain tools that amplify human capabilities rather than replacements for human judgment, though the temptation to defer decisions to algorithms that process data faster and seemingly more objectively than humans remains persistently present. The industrial base required to manufacture systems like the CS-5000T presents strategic vulnerabilities that extend beyond the immediate platforms to encompass the specialized suppliers providing components, materials, and subsystems. Radar-absorbent materials come from limited suppliers with specialized synthesis capabilities and quality control processes that cannot be quickly replicated if production capacity needs to expand or if supply chains face disruption. High-performance composite materials require precursor materials like specialized carbon fibers that few manufacturers produce, creating single points of failure where disruption of one facility impacts entire production programs. Precision machining and assembly of components like sensor gimbals and control surface actuators depends on skilled technicians using specialized equipment, capabilities that require years to develop and cannot be surge-produced when demand increases. Electronic components, particularly specialized processors and infrared sensors, depend on semiconductor fabrication capabilities concentrated in limited geographic regions subject to potential disruption through either natural disasters or deliberate action. These industrial dependencies mean that platform capabilities in extended conflicts may be constrained less by design performance than by ability to sustain production rates and provide replacement units as combat losses and accumulated maintenance requirements deplete operational inventories. Environmental operating conditions impose constraints on system performance that promotional literature tends to minimize, while operational commanders discover uncomfortably during actual employment. Temperature extremes affect everything from battery performance and electronic reliability to composite material properties and lubricant viscosity in mechanical systems, with both cold environments causing brittle failures and hot conditions producing thermal expansion mismatches. Humidity and precipitation influence radar-absorbent material performance, create condensation issues in sealed electronic compartments, and degrade electro-optical sensor effectiveness through atmospheric attenuation. Dust and particulate contamination affect turbofan engine performance by eroding compressor blades, clogging cooling passages, and depositing on optical surfaces, requiring more frequent maintenance in arid environments than pristine test ranges. Icing conditions create aerodynamic and engine intake hazards that demand either operational restrictions or specialized protection systems that add weight and complexity. Electromagnetic environments containing friendly high-power emitters can saturate receiver front ends or create interference that degrades sensor performance, requiring coordination and potentially geographic separation between different electronic systems. Altitude and air density variations affect aerodynamic performance, engine thrust, and cooling capacity in ways that restrict operational envelopes more severely than simplified performance specifications might suggest. The economics of unmanned platforms versus manned aviation continue generating debate that mixes legitimate analysis with institutional interests and service rivalries. Unmanned systems avoid placing air crews at risk, eliminating concerns about pilot survival, recovery, and potential capture that constrain employment of manned platforms in high-threat environments. The absence of cockpits, ejection systems, and life support equipment reduces weight and volume that can instead accommodate fuel, sensors, or weapons, improving performance or capability within a given size class. Endurance can extend beyond the limits imposed by pilot fatigue and human physiological requirements, enabling persistence that manned platforms cannot match without multiple crews and in-flight refueling. However, manned platforms provide onboard decision-making, adaptability, and situational awareness that ground-based controllers separated from the immediate tactical environment may lack, particularly when communication delays or disruptions prevent real-time interaction. The cost comparisons prove more complex than often suggested, given that unmanned systems require extensive ground support infrastructure, communication networks, and maintenance workloads that may rival or exceed manned platform requirements when examined comprehensively rather than comparing only flyaway airframe costs. Ultimately, the CS-5000T represents an instantiation of broader trends in military technology toward distributed sensors, network decision-making, and increasingly autonomous systems that promise to transform warfare while introducing new vulnerabilities and operational challenges. The platform's stealth characteristics provide survivability advantages in specific tactical situations, while remaining vulnerable to evolving detection technologies and degrading rapidly if maintenance standards slip or if material properties degrade through environmental exposure or battle damage. The sensor suite delivers reconnaissance capabilities that tactical commanders previously could not access without requesting support from higher echelons, potentially accelerating decision cycles and improving tactical understanding, but also increasing data volumes that can overwhelm analytic capacity without corresponding investments in processing infrastructure and trained personnel. The strike capability provides responsive kinetic options, but also raises questions about engagement authorities, rules of engagement implementation, and the risks of hasty action against misidentified targets. The artificial intelligence autopilot automates routine functions and manages complex flight behaviors, freeing operators to focus on mission execution rather than aircraft handling, yet creates dependencies on software that may behave unpredictably in situations outside its training envelope and introduces cyber vulnerabilities through the complexity of modern code bases. Whether the CS-5000T and similar platforms prove transformational or merely incrementally useful depends less on their inherent technical capabilities than on the doctrinal imagination applied to their employment, the training invested in their operators, the sustainability of their support infrastructure, and the specific characteristics of conflicts where they face deployment, all of which remain uncertain until actual operations test theoretical capabilities against hostile resistance and operational friction.